Good afternoon, everyone. My name is Haokun Lee. I graduated from UC Berkeley in Professor Xiang Zhang's group. Then I joined Stanford as a postdoc. Now I work at Apple as a hardware engineer. So very happy to see all of you. I'm very happy to present here on behalf of my previous advisor. Today I'm going to talk about our work regarding Casimir force. And I'll talk about two work. One is regarding Phonon coupling, and the other is about mechanical stable equilibrium, both through the Casimir force. So first off, I will give you a very brief intro of Casimir force. I believe Professor Monday and also another professor gave a very nice introduction in the morning regarding Casimir force from both theoretical and experimental side. And I'll just give a very simple recapture of the general idea. Is that when you have like a general neutral objects, if you place them very close to each other on the order of nanometer separation, you'll see them, they start to attract each other. So it's very bizarre phenomenon if you think intuitively, and it has a very deep fundamental relation to quantum physics. That, for example, if you have all the matter are made of atom, and so atom in general, they are neutral particles, so they shouldn't like generally attract each other. But if there are like fluctuation or quantum fluctuation of electric field, then one atom may become polarized at one instant. And then if this atom gets polarized, then the electron cloud may attract the nucleus of the other atom. So they will talk to each other. So it generates this configuration where you have an electron cloud and also neutral nucleus. They are very close to each other, and the polarization of these two atoms will attract to each other. So you end up with this configuration where atoms are attracted to each other. At the instant of one atom become polarized by fluctuating electric field. So I like this picture because it's very intuitive and explains the physics well. And if you have and then if you consider like all the objects, they are made of atoms, so you can sum all the interactions between all the atoms in objects. Then you end up with these attractive interactions between the objects. And today I'll be, and for example, for two metallic plates, there are two regimes people generally consider. One is called the Van der Waals regime, where the separation is below 100 nanometer. And then there's another region which we call the Casimir region. And they have different scaling law, because in the Casimir region, you have to consider like retardation or other effects of electromagnetic fields. And very importantly is that this force will compare to like atmosphere pressure or electrostatic force. It becomes prominent at nanometer scale. For example, 10 nanometer, it's equivalent to 1 atmosphere pressure. So it's very important to like nanoscale devices, for example, nanoelectronics and or MEMS devices, where engineering this force and also heat transfer will become very important to the nano field. So today I'll talk about two recent experiments that we performed at Berkeley. One is regarding Casimir Phonon coupling. The other is about stable equilibrium and trapping. So let me start by giving you a very brief recap of the conventional concept of like heat transfer. If you put two objects and make them into contact, then you have conduction theory to describe heat transfer, and energy is transported through the vibration of the lattice, so-called phonons or electrons. But if you separate the two objects and make them far from each other, then you have radiation, which energy is transported by photons. But usually phonons in like conventional concept is they don't like travel across the vacuum because you need a medium to like make them couple to each other. While because of this Casimir force, and there are many recent theory on this topic. If you think about like you have two objects with different temperature, and you try to place them with a nanoscale gap, then for example, one object, then because of you think about the two objects have finite temperatures, then their surface must be like vibrating, and then and because there's a Casimir force between the surfaces, so the vibration will start to talk to each other due to the gradient of the Casimir force. So equivalently, you can think about there is a spring that connects the Phonon modes between the objects, and the spring constant is proportional to the Casimir force gradient. And so there are many recent theory describing this phenomena. And so mathematically, you can think about this. There are many Phonon modes, and you add up all of their coupling to consider the energy transfer from one side to the other. And there is a prediction where this Casimir Phonon coupling may exceed like near field thermal radiation with a gap on the order of like sub-nanometer to a few nanometers. So it's not a fully understood phenomena, but it's very interesting to people can just start to think about it or measure it experimentally. But we consider this as like both a challenging thing, and also there's an opportunity to first to like identify this phenomena, the Phonon coupling through Casimir force, as a like first of all demonstration. Because if you want to measure like the full bulk body transfer, you need to make like the two objects very close with a sub-nanometer to nanometer gap, and you have to consider like electron tunneling or charge-charge interaction between the solids. So it remains like a very challenging problem. We consider this use like individual Phonon modes between the objects, so that you can look at only the thermodynamics of individual mode vibrations, and then you can separate or single out the phenomena very well through optical mechanical measurements. So that's our idea of our work. So let me give you a very brief intro about like how people describe single mode vibration. I believe many people in this room are from heat transfer area, but I did my PhD studying from atomic physics, so I know like laser cooling of atoms or ions, where people use lasers or something to cool down individual in single degree of freedom, for example, atoms, or even mechanical objects like vibration cantilevers, and describe their thermodynamics. For example, if you have a mechanical membrane in vacuum, and if there's nothing around, and there's like a fundamental vibrational mode here, it's like a drum here, and if this membrane is placed in vacuum and there's nothing around, the mode vibration can be it's kind of the amplitude is bouncing up and down, and the phase is irregular, and you can measure actually the displacement of this particular vibrational mode as shown on this figure, and the average mean squared amplitude of this vibration mode can be used to describe its kinetic energy, or you can use like equivalent mode temperature to describe how much energy it's stored in this particular mode, right? And there are also circumstances where you can do some engineering, or you can use lasers or other type of things to either kick this mode or cool down this mode, so that it can have a different vibrational amplitude than its equilibrium case, so that it can exchange energy with its thermal bath, which is all of the other Phonon modes inside this particular membrane. And the exchange rate is determined by the temperature, mode temperature, and subtracted by the bath temperature, and it's multiplied by the damping rate, that you can measure how much energy is decaying from this mode, right? So in this experiment, we place two mechanical membrane very close to each other, and we look at the vibration of these two fundamental modes from these two membranes here, and we match their resonant frequency. And at the beginning, we separate them, and then we match their frequency. At the same time, we put them at different temperatures. So if they are separated very far away, the mode temperature will be equivalent to their own bath temperature. But if you place them very close to each other, because the modes start to talk to each other very strongly through the Casimir force, then and if this coupling is exceeding the damping rate of this vibrational mode, then these two modes will become like more like an equilibrium case. They start to their mode temperatures start to merge at very small distance.
It is an experimental theory.
So this is our theoretical prediction, and we will show our experimental results soon. Yeah.
The temperature T prime and T prime will be very different.
What? Sorry?
Equipotential law is a law which forms in equilibrium, but the temperature is constant. So you are assuming that both temperatures are different. No?
I'm assuming, sorry, what?
The temperature, I mean, T prime, the temperature is different from the temperature of the bath.
Yes,
right?
That's right.
And then, the equipotential law you formulate here is strictly valid when the system.
I think.
The mass, the volume of the mass.
No, because people.
I'm sorry. I was telling you that this equipotential law is strictly valid when the temperatures are constant. The temperature of the system is equal to the temperature of the bath, right? If this is not so, in principle, for a very large differences of temperatures, is not valid in general. So you are assuming that the temperatures are not very different, I would say. But what is the value of the temperatures you consider?
You mean the validity of this mode temperature when it's far from this their own equilibrium temperature? You can view it as like thermal energy stored in this particular mode, right? Because it's still if you look at the distribution if you look at the mode dynamics, and if you look at the distribution of this displacement versus time, it still follows Boltzmann's distribution. So there's also, if you look deep inside, there's a whole mathematical description about single mode and their entropy and so on, that you can think about. There's some validity of this mode temperature still, if it's still far away from the equilibrium temperature. Okay. So this is basically what we need to measure is the average displacement of the mode, so that we know how much thermal energy is changed within this particular mode. So we use laser interferometry, where we park our laser. There is a 50-50 mirror, and we separate them with the membrane, and it forms like partially a Fabry-Perot cavity, and you can measure the reflectance change versus time, so that you know how much vibration it has. And we can measure that down to like picometer precision, which is like 100 times smaller than the size of an atom. So this is the experimental setup where we have two silicon nitride membrane, and they are suspended on top of a silicon wafer. And we coat both sides with gold, so that to enhance the Casimir interaction. And to place the two membrane very close to each other, we made them one of the membrane as a meso structure, and the other one we have 4 electrode pads where they are used to align them parallel to each other. And there is a cooler and heater and also temperature sensor. And that temperature sensor is to measure the bath temperature or the body temperature of the membrane. And the mode temperature or the mechanical displacement are measured by the laser interferometry here. And a very important requirement to make this thing work is to make the resonant frequency of these two particular modes, the mode on the fundamental mode on the left side of the membrane and fundamental mode of the right membrane, have the same resonant frequency so that the vibration can really talk to each other. So, and this is by this is achieved through thermal tuning of stress, where we intentionally design the membrane so that they have slightly different size, but we heat up one of the membrane while cooling down the other membrane, so that use the thermal stress to tune their mechanical frequency and make them the same. At the same time, we establish there's a temperature gradient across the membrane, so that we can really make the mechanical mode talk to each other. And so this is some little more details regarding how we align these membranes, and we use both the electro paths to make sure that they all contact with the mesa structure. At the same time, we use LED to look through the membrane, use with blue light, so that so this is optical interference measurement, where if the membranes are slightly tilted, you will see those interference patterns are inhomogeneous. While if they are very parallel to each other, then you will see at the left top where the two membranes are really parallel to each other, so that we can achieve like plus minus milli radian precision. Because the membrane size, lateral size about a few hundred microns, but we put them as close as 300 to 400 nanometer. It's 1 to 1,000 ratio of parallel adjustment. And this is our experimental results, where the left figure shows the vibrational spectrum of the one of the membrane when the two membranes get put close to each other, where you see like kind of two bands. The upper band is like the symmetric mode, where the lower band is like the anti-symmetric mode of the membrane. And we use a voltage between the membrane to compensate for the electrostatic force. Because even if you have two metal plates, they are neutral, you still have like residue of electrostatic force. And we use that voltage to compensate that. And you can see at a certain voltage, even the electrostatic force is compensated, you still see like a splitting of the modes, which indicates there's a residue of coupling. And I plotted on the middle side of the figure. And if you plot the coupling versus the distance, and you see clearly there's a scaling law that is roughly proportional to the d to the -5, which indicates that the coupling is type of a Casimir coupling that agrees with the parallel plate theory. And this is the main results from the displacement measurement, where when we separate the two membranes and make them far away from each other, the mode temperature is kind of equal to the bath temperature. While if we put them close to each other, the mode temperature start to merge, meaning that the vibration of one mode start to like vibrate less, while the other mode start to vibrate more. But the bath temperature, because they are like hundreds of nanometers, the bath temperature doesn't change that much. Maybe 1 milli Kelvin or less. So, and this is to distinguish, like for example, other effects, because this experiment requires the Phonon modes really talk to each other. So if we make them off resonance to each other, then we don't. The experiment shows that there is no like change of mode temperature. The Phonon modes are still in equilibrium with their respective thermal bath. So to briefly summarize this work, we observed heat transfer or Phonon coupling across the vacuum through Casimir force for the first time, and we distinguish this from electrostatic force by looking at the force gradient, and also we use electrostatic voltage to compensate that effect. And also we one thing to highlight is that we observe a strong Casimir phonon coupling, because we see the splitting of the vibrational modes, and that indicates that the coupling already exceeds the damping rates of the mechanical vibration. And we look forward to new experiments to look at when majority of the phonon modes are precipitating, and to observe heat transfer between bulk solids. So let's finish up the first part of my talk. And the second part of my talk is about stable equilibrium or trapping. In my introduction, I talked about Casimir force, and in many cases they tend to be attractive. This is how geckos can walk on glass, and there are many interesting phenomena. But also you can engineer nanostructures to make Casimir force being repulsive. And there's a famous experiment demonstrated by Professor Monday with Capasso at Harvard, where you can use a different material with different electropermittivity to make this ball being repulsed by the substrate. And very intuitive picture is that in general, because if you think about the picture, the dipole-dipole interaction, they're always attractive. So how can you make a repulsive force? Is that you need this fluidic environment where you have a different dielectric constant, and you make the fluidic environment very much like the ball, so that it really likes it, so that it doesn't want the substrate to attract it. So that it the fluid push the first object upwards. So that's more like an intuitive explanation. And the question we want to ask is that, okay, we have this attractive force and we have a repulsive force. Is there any possibility to achieve trapping through Casimir force, so that you can have levitation or other or floating phenomena with quantum vacuum, so that you can potentially prevent friction or other energy losses in nanostructures or MEMS. So we designed this 4-body structure where you can think about the upper 3 parts, the body, the environment, and low index coating is very much looks similar to the repulsive structure. But you have another body 2 which have a relative high dielectric constant. Okay, so when body 1 is very far from the whole substrate, then it views the low index coating and the body 2 as a whole structure. And because low index coating has pretty low index, so it doesn't have much effect. So when they separate far away from each other, the body 1 still see a whole structure, and it sees body 2 more. So the force is more attractive. But
Thank you. Is it a broadband low index coating?
What's that?
Is it a broadband low index coating or for one single frequency?
Broadband, yeah. Because Casimir is you have to integrate all the electromagnetic frequencies to get the force. Right?
And how broad it is? How broad?
That's a good question. I think all the material, it comes back to our original introduction of Casimir force, is to what frequency you have. Usually for optical material, they have plasmonic frequency on the order of the wavelengths on the order of 200 nanometer-ish. Because you think about the integration, it's all integrated from static region to very high frequency region. But if frequency is too high, then the material wouldn't respond, right? But high frequency, they have more density of states. electromagnetic densities of this. So they contribute more. So most of the contribution of Casimir force is close to the plasmonic frequency, but you cannot go beyond to that because the frequency is too high, the material wouldn't respond. Does that make sense to you? Okay. Okay. But if you put the body one very close to the low index coating, then you can imagine this three-body interaction, like the competition between the attraction will play an important role here. And that actually agrees with our calculation, where the red curve is the total Casimir energy of the four-body structure, while the green curve is when we remove the body tool in the calculation. And it agrees well with the red curve at small distance. But also the blue curve is the calculation without the low index coating. So it agrees well with the red curve at far distance. And this is our experimental design where we have a thin gold plate, and the low index coating is through Teflon, and there's another gold substrate. And we put the gold plate inside the ETOH liquid. Basically we grow the gold thin film, and then we put them into ETH, and we drop cast into this cover glass, which there is O-ring on the top of it. And then we put another cover glass to seal the device. And so to observe the trapping phenomena, we put the whole thing upside down, and we look at it with a microscope. And if there are a few of the gold plate which, due to gravity, they may fall onto the bottom of the microscope, but we see like many of the gold plates, they're kind of levitated, and they are doing like two-dimensional Brownian motion like this, and we can track their position, and it goes to like a Brownian trajectory. So to quantify this phenomena, we can measure the distance between the gold plate and the Teflon, so that we know that it can matches our like Casimir calculation, and to indicate this will be a Casimir force trapping. And we measure it also through optical interference, where you can think about this gold plate and also the Teflon forms optical cavity, and there is a resonance effect. And the resonance dip here, you can calculate that with different separation. And for example, here we measured the resonance dip is around like 545, and that agrees with a trapping distance about 45 nanometer. And also we did experiment with different Teflon thickness that actually can result in different trapping distance, and that we measure like different trapping distance, and that agrees with the theory prediction. To summarize the second part of the talk, we have demonstrated the Casimir equilibrium or trapping for the first time, and hopefully this can be used in like contact-free nano devices in the future. And thank you very much for your attention, and I want to thank all of the audience who attended my talk, and all my collaborators and the team. We work together at Berkeley, and also the funding agency that support us. Yeah, thank you very much. I look forward to your questions.
So we have time.
Yeah, so thank you very much for your talk. Very impressive experiments. So these membranes, what are they made of? And whether the material matters for this vacuum Casimir force? What material did you use, and how the material constants enter there?
Yeah, mostly in Casimir experiment we use gold, because for the first experiment we coat both sides 75 nanometer, and the second experiment was like the thickness of the gold plate is around 50 to 100 nanometer.
Thank you for an interesting talk. I was wondering, during the first part when you're talking about the fluctuations and giving that you get from the Phonon contributions, I was wondering, so if you have a bulk material and you've got phonons that are there, it looked like you're showing that kind of the gap between the two surfaces is locally changing at different points due to these phonons kind of deforming the surface. And I was wondering if that has been looked into with the Casimir force as to how that actually changes the Casimir force in addition to the heat transfer.
Exactly. That's a very good question. Actually, if you look at those theory paper, so because in our case, we look at the fundamental mode and our separation is huge. So we use this local parallel approximation. But it's not the case if you put the two objects with separation like below nanometer, and those vibrations can have a large effect of the surface curvature, where Pendry's paper here, they include that into effect so that you may have different scaling law of the heat transfer due to that. So yeah, definitely you need to consider that if in that particular region. But for our experiment, we don't have to do that because it's fundamental mode and vibration compared to the separation, it's very small.
Yeah, interesting. I was wondering, even beyond the heat transfer, just for the Casimir force in general, it would seem that it would be similar to correction that you'd have for like the roughness correction on the Casimir force, but that would be due to the phonon modes as opposed to due to actual roughness. And it would seem to be dynamic as well, and so I wasn't sure if that would have another implication. Because it would be a thermal effect in that it would be dependent upon temperature because you have to excite these phonon modes. But at the same time, it's not a thermal Casimir effect because it's not due to thermal fluctuations that are giving rise to like kind of photons. It's actually due to variations in the surface separation, which then affect the quantum fluctuations. So I just thought it sounded like an interesting problem. I wasn't sure if there's been much work on that. So thank you.
Go ahead.
Yeah, in the experiment of the Brownian motion, you mentioned it. The particle moves in a confined region, no? I suppose. You know, it's confined Brownian motion, no?
The plate.
Yeah, between the plates, yes.
It's only confined in Z direction, but XY we don't have trapping effect, so it moves freely.
Yeah, but the mean free path is much smaller than the distance of the plates between the plates, I suppose. Because if not, you should include the friction coefficient is changes, so it's not a constant. For a Brownian particle moving in an unbounded medium, the friction coefficient is a constant. Depends on the viscosity and depends on the geometry of the particle. But if you reduce the space and the Brownian motion is confined, the friction coefficient depends on the interaction between the particle and the walls. So it's not a constant. Suppose that in your case, yeah, you have considered it as a constant, and according to the experiments, it works very well.
Yeah, we have only confinement in Z direction. The XY we don't have confinement. Are you saying that the Z confinement will affect the mean free path of the XY direction potentially?
Mm-hmm. Mm-hmm.
Yeah, because for us we don't have like a comparison with that. You can measure the mean free path, but you need the baseline to make a comparison. Yeah, but that's a very good point that we could look at in the future.
Thank you.
Thank you. My question is actually along what Jeremy was saying. I was wondering if you could elaborate a little bit more on the mechanism phonons are coupled to the Casimir interaction, because phonons, as was pointed out, require temperature but also medium. So I don't see how that couples to the electromagnetic nature of the Casimir interaction, other than the fact that maybe the boundary conditions change because there is some kind of a roughness-like behavior of the surface.
Okay,
Or
I try
unless,
to answer this question in a way that.
So in that sense, you didn't actually measure the Casimir force due to phonons. You measured heat transfer, correct? In your experiments, when you talked about the Casimir phonon part, what did you measure? You measured heat transfer, correct? Or Casimir interaction?
Casimir interaction, and also the thermal energy stored in that mode. Yeah. The heat flux is calculated through measuring the energy stored in that particular mode and also the damping rate. So I multiply that to calculate the heat flux. But you have to trust the single mode dynamics theory to validate that.
So my question is, what's the mechanism of the coupling between this electromagnetic type of interaction with phonons? Because phonons require medium and non-zero temperature. So what couples to what? That was my question. I guess I think Jeremy already, talked about the surface wavy-like motion because of phonons, but other than that, I can't see any other mechanism of coupling.
No, phonon doesn't require temperature to exist. It's a mode, right?
Well, you need to have it at temperature that's not zero, because if it's zero, you have no phonons, correct?
The coupling, if you have zero temperature, you can still have coupling between the phonon mode, right? The mode still exists.
How?
It's
they're not excited,
eigenmode
right?
of the mode exists no matter what kind of temperature you have. Right?
Phonons have, if you have zero temperature, you have no phonons.
No, the mode isn't excited, but the mode still exists.
Then how do you manifest it if it's not excited? I don't see it.
No, we measure the whole thing at room temperature, so the vibration.
Room temperature, not zero.
Yeah. That's right.
Okay, so my question still stands. Actually, I don't know, maybe I'm not understanding something.
Yeah, we can talk more, offline, yeah.
On the first part, you told us that you have measured the heat flux, the heat transfer, as you say. So do you have an order of magnitude of this transfer at the end? What is the flux finally? Because I didn't see any curve of heat flux in your presentation. So do you have the value of this flux, and can you compare it with the prediction of the Ritov theory, for instance?
So this is our, so we measure the vibration of the mode, and then so the heat flux is calculated by the difference between the mode temperature and the mass temperature, and we multiply it by the damping rate. So if you want to get a heat flux, that's our estimation.
And compared to the Ritov theory?
What's that?
The Ritov theory, the fluctuational electrodynamics. What is the value you get in this case and compared to the classical fluctuational electrodynamics? You have an idea, or? Okay, we can discuss after if you want.
Yeah.
Just, I guess, just a comment. I think what's the coupling mechanism? Just a mode coupling, electromagnetic wave coupling of the single mode, right? So that's you think that's Casimir, but it's a single mode. You don't need to sum up all the heat flux.
Yes. So if you have neutral, there may be different type of phonons. So if it's deformation potential phonons, they're neutral. They don't carry any charge. So,
but the dipole interact, right? Even you have dipoles. dipole, if one side dipole vibrate, and it will affect the other side through just the same Casimir interaction mechanism. I guess my question is for the Z direction that the equilibrium. Did you measure the fluctuation in the Z direction? Do you have that?
We have
Z variance. Or
we have a. Let's see. The Z.
I guess you got the view. Oh, okay.
Yeah.
Okay, so that's you take an average. That's your variance there.
Yeah, you can compare that with your trap depth and the temperature to see the mean squared, if that agrees.
Could you speak there?
I mean, is there a proof of the fluctuation dissipation theorem in the case of phonons?
Which one?
Yeah, the fluctuation dissipation theorem, as Philippe mentioned it. I don't think that is a proof of that. Yeah.
Proof of what?
Okay, we can talk later.
Yeah.
Still have time for one short question.
Thanks for the talk. I have a question about the Brownian motion in the XY. Did you happen to measure if you measure the angular deviation of the gold flake, since you have XY symmetry, you should also see that the angular deviation shows Brownian motion. Did you measure it?
So you mean
the flake is also rotating, right?
We don't see it. We don't have measurement on the rotation.
Still one final question. Anyone? So follow up on this question about the Brownian fluctuation along Z. So you could have the stiffness, right, of this K of this associated equilibrium from this variance. But have you compared with the variance of the Z Brownian Z variance?
I need to check. Yeah.
Okay, I think we can stop here then. Thank you. Let's speak. Thank you.